set, right, is to calculate the distribution of beta. Now, if it's a normal distribution, what is it governed by? It is governed by what? It is governed by the covariance matrix, right? So in order for you to calculate the beta distribution, you want the covariance matrix. You know already the expected values, the 1.8%, etc. What you want to do, you want to calculate the covariance matrix of beta. So what is the covariance matrix of beta? The covariance matrix of beta has the following formula. It's covariance of the factor inverse times sigma epsilon squared divided by n. Okay? It's covariance of beta equals to covariance of F inverse times the residual divided by n. In one dimension, this formula reduces to the following. That variance of beta, okay, equals to what? To covariance of, to sigma epsilon squared divided by n times variance of x. Okay? In other words, sigma beta equals to sigma epsilon divided by square root of n times variance times sigma x. That's exactly the formula, right? That I gave you last time. What I'm doing now, I'm actually generalizing this formula. Okay, now you can actually take it from here. What you want to do, you want to actually create a summary. If you do summary, so here you do the linear model and you do summary of the linear model. Like this. You will see, right, the standard errors of the betas here. The standard errors are the sigmas. Okay? Is this clear? So how do you actually read the sigmas from this crazy formula? How do you read these sigma betas from this crazy formula? Anybody can tell me? How, if I have a covariance matrix, right, of factors, how do I know the sigmas? How do I know the variance? Exactly, very good. But it's not just the, the Wisconsin guys that should answer it. Remember that covariance of beta 1, covariance of beta 1, beta 2, and covariance of beta 1, beta 3. Then covariance of beta 1, beta 2, beta 2, beta 1, covariance of beta 2, beta 1, beta 2, beta 2, beta 2, and covariance beta 2, beta 3, and the last one is covariance of beta 3, beta 1, covariance of beta 2, beta 3, and covariance of beta 3, beta 3. Right? The diagonal are the variances. You know the variances, how do you take the sigmas? How do you find the sigmas from the variances? What do you do? Exactly, square root, excellent. Okay? So you need to find the covariance matrix, you need to look at the diagonal. This is your variance, and then you take the square root of the variance. Is this clear? Good. So, for us to find the 95, to find this 95% confidence, I'm going to talk about it in a moment, right? You want to find the covariance, so we are going to use this formula now, and then we are going to compare this to these beauties. And let's see where we're going. Now, by the way, what does this thing give you that this summary doesn't give you? What does this thing give you that this summary doesn't give you? When you look at this, what does it give you that this summary doesn't give you?
Covariances?
Exactly, right? Those guys here, how covariance beta 1 and beta 2 are interacting? Covariance of beta 1 and beta 3, right? So if you have the first coefficient and you have the third coefficient, you want to understand how they interact together. And these guys doesn't give it to you because it gives you just a diagonal. It doesn't give you those kind of, it doesn't give you those kind of things. So this formula actually contains much more information. It's just the people, right, that are doing regressions do not care about that, and they just care about, the distribution of single value of the coefficients, of just the coefficients. They do not care about, the interaction between the coefficients. Okay? Is this clear? Questions? Is this clear? Right? So you have three coefficients. And they're also multi-distributed, right? So once again, this formula, what does it depend on? This formula depends on the fact, right, that f stays the same. So when I'm actually looking at this formula, I'm not moving those guys. The only thing that I'm simulating is the epsilon. It's exactly like in the one-dimensional case. Remember, in the one-dimensional case, when I played this game, I had y equals to beta 1 f1 plus alpha plus epsilon, right? What I did, I just simulated this part. I did not touch this part when I actually calculated the distribution of beta. Remember how I did it, right? So I simulated one instance, right? What I did last time. I simulated one instance, so let me just repeat what I did last time. Okay? Or what I tried to do last time. So let's just repeat it again. Okay? So what I did last time, right? I took two variables and I run one against the other. So it's going to be a 2x2 covariance matrix. So it's going to be covariance. So let's take covariance F. This is going to be column bind of, let's say, 0.4, 0.2, 0.2, C 0.4, 0.2, and here it is going to be C 0.2, 0.5, let's say. So what is CF? Now what I'm going to do, and let's say that expected value, okay, so let's say that, so I have this matrix, right, and the expected value of the first one is going to be 0, the expected value of the second one is going to be 2. So now I'm going to simulate, right? I will say MVR norm, okay? And now I will say, all right, I have MVR norm, all right? So I'm going to simulate now 1,000 points, 10,000 points with 0.2, right? And my covariance is going to be CF. And I will put it into XX. Okay, so this is your XX, right? So now I will run the regression of XX, comma 1, of XX, comma 2, versus xx comma 1. And I will do a summary. Okay? So I have the intercept and I have the beta here, right? So now, if I look at CF and I want to calculate beta independently, what do I need to do? I need to take, so I need to take the covariance between x1 and x2 and divide by the variance. So I have here that it's going to be 0.2 divided by 0.4, which is 0.5, which is pretty close to this number. Okay. This number is going to be exact. To your questions, this number is going to be exact. How do I make this number exact? I will do covariance of xx comma 1 with xx comma 2. Okay, and I will divide by the variance of x1, of xx comma 1, like this. I get the same number of here. Okay, because when I simulate, right, it's not exactly going to be CF. So if I look at CF, this is my CF. But if I look at the matrix covar of xx comma 1 and xx comma 2, watch what will happen. Right? You can see that it's not the same. Is this clear? Right? It is not the same because the simulated thing will never be the same. Okay? Any questions?
Okay, so my and are more.
Yes, absolutely. For the second case, right? Or the first case?
For the second case.
Good job. Now, how do I find the residue, right? How do I find the standard deviation of the residue? I told you that the formula is going to be var, in this case, is var of y minus beta 1 square var of f1. Okay? And you can actually, and we are going in a moment to see what is the corresponding formula in the higher dimensional case. Okay? But just keep in mind this formula. So we're having variance of y minus beta 1 square minus var f1, right? So when I'm actually going to do that, so let's do it. So what is var of f1? Var of f1, var of y is 0.5, right? So it's 0.5 minus, and we said what is my beta? What did we say is my beta is? 0.5, I think. So it's 0.25 times, right, the variance of f1, which is 0.4, and your variance of the residual is 0.4, right? So what is the square root of 0.4? Is 0.6324. And now watch here. Where's my residual? This is my residual. This is my residual standard error. Okay? If you want to nail the correct, the exact result, watch the magic, right? So I will take, what do I need to take? I need to take the var of xx comma 2 minus, and now I will take my my beta, which is this guy, square, and I'm going to multiply by the variance of x11, which is going to be what? I don't know what it's going to be. I'll just say var of xx comma 1. And I will probably take var. Sometimes R is funky. Zero point 703807. Little bit different than this, I don't like it. What did I do wrong? So xx comma 2. So what is variance of xx comma 2? Okay. So it's 0.5. Is this correct? Yes, it's 0.5. So var of xx minus 2 divided times my beta. So I said that my beta is this guy. Square, and then times var of xx comma 1. So this is 0.3952, and what is my standard error? The residual standard error is 0.06.287, so I take square root of this. And hopefully I will get, yes, right? 0.6287, here you get 0.628694. Questions? And the problem was that here, right, it wasn't the correct coefficient. This is the correct coefficient. Okay? Questions? Is this clear? So now going back, right? So now when I actually trying to get the distribution of beta, I simulate the epsilon. I'm not touching this. Okay? I'm not touching this guy. I'm simulating just the epsilon to get this number here. I just simulate the epsilon. Okay? So let's say that you simulate the epsilon. Okay, so you just do R norm. What is the expected value of epsilon, by the way? It's 0, right? So you have how many points I got here? 10,000 points or something? 10,000, right? I simulate, let's say, 100 instances of epsilon. To generate the betas, I need more, right? So I generate 100 instances of epsilon. I know that it's not easy, you know, but that's okay. I have faith in you. And now I'm going to take the standard error from here. Where's my standard error? This is my standard error. Okay? And I need columns. And we say here that it's sim-resi. Right? So if I look on sim-resi, 10,100. So I generated 100 instances of what? Of the residual. And now, right, what I'm going to do, I'm going to add to these 100 instances of the residual one instance of xx comma 1. You see, I'm not simulating xx comma 1. That's a crucial point here. Because usually you can simulate, it's details. It's all about details, guys. Right? You could say, oh my God, I want to simulate xx comma 1. No. Because if you simulate xx comma 1, then it won't be conditional on xx comma 1. What does it mean to be conditional on xx comma 1? It means that when you play this game, you are not simulating xx comma 1. You just simulate the residue. And now, how do you simulate the y? Right? You are going to take your beta, which is this guy, you're going to multiply by xx comma 1, and you're going to add the sim residue. And this is going to be sim xx comma 2, like this. Voila. What do you mean xx sim xx comma 2? Here. Okay, I see. All right. Like this. Voila. Questions? Questions? Is clear? Questions? Is this clear? It's all about details, slightly. It's all about details. Right? Yes?
So you say it's better to use the linear regression method?
Absolutely. Well, I'm using the linear regression method here. What I'm doing, right, I'm looking at the statistical properties of the result.
The first one, I mean, the one is linear.
Well, no, of course not. But that's what you're doing here, right? You're simulating what you see. You're simulating the second, the variable, right, to compare it to something. Okay. Now the question is how you simulate, and how you simulate. You are actually simulating just the residue, and you keep the xx1 intact. So if you actually think about xx101, you download the stocks. You download 2 stocks, right? Or you download the index. You're not touching the index. So when you are looking at the CAPM, right, you basically have one stock, which is going to be beta times the index plus alpha plus epsilon, right? When you are actually looking at the distributions of beta, you are not going to touch the index. The index will be the same. You can think about this xx comma 1. What you are actually going to just to simulate is just the epsilon. Okay? Is this clear? Is this clear? I know that people don't do it, even in, when they actually teach statistics, they don't go into this kind of details, but that's okay. That's why you have me. Okay. Questions? Okay, now, how do I generate the betas, right? What I want to do, I want to run sim xx2, each column, I'm running it against xx comma 1, so to generate the betas. Okay? But for that you need to actually find the second one, the beta. So that's why you want to have the coefficients there, right? That's why you need to create a function. So let's say GG is a function. So I think it's let's see, it's a coefficient. xx comma 2 with xx comma 1, right? So you want the second coefficient. And now you have you need to generate a function, right? So I call this function GG. And then you have two parameters. You have U and V. So then your function will be coefficients of linear model of U versus V, okay? Second one. So now you can actually apply this function on xx comma 2 and xx comma 1. So you can say GG, right? And now you have xx comma 2, the second one, and xx comma 1, the first one. Okay? You want to put it here like this. What about this? What? What is that? Maybe I need another one. Voila. You see, I get the same result, right? So what I'm going to do now, I'm going to simulate the sim resid versus x comma 1. So watch. So I'm going to do apply on sim resid. How did I call it sim resid? Sim xx. Apply on sim xx, and you want to apply to columns. And what do you want to apply? You want to apply the function GG, but you want the V, right? You want the V to be xx comma 1. So what this function, what apply is doing, right? I told you that apply tells, so you have a matrix of columns, of 100 columns. What apply does, it says to R, take every one of those guys. Think about this as a dependent variable and run a regression against xx comma 1. Okay? And it's a nightmare to do it in Python. It's doable in Python, but it's a freaking nightmare. You have to have a for loop, and it's a nightmare. Okay? So I'm doing it in here, and I will put the result, and I will put it in res. What do you mean it's not found? What is simxx? Simxx2, okay. Is it found now? Yes, yes, it's found, it's found. Hist of res. Voila, you see? This is the betas. These are the betas. This is a God's eye, right? These are your betas. Simulated betas. Simulated betas. Why is it so choppy? Because it's only 100 points. Right? If I have 10,000 points and I have a million things, right? It's only 100 columns. But you can see exactly the logic here, right? I simulated only the epsilon. And keep this fixed. I'm not touching this guy. Is this clear? Questions? What is the standard deviation of res? Because that's your betas, right? So the standard deviation of res is 0.0110812. So now let's do linear model summary. Linear model xx comma 2 tilde xx comma 1. Voila. Pretty close. This is a theoretical value, right? This is a simulated value, so it will never be the same, but you can see that it's pretty close. 0.0101826 and 0.011033. And when you simulate, you should get little bit different numbers, but they need to be close. Whatever close means, right? So you can see that it's 0, 1, 0, and this is 1, 0, 1. Pretty close. Questions? Questions? It's subtle. It's subtle. Okay. So going back to this case, it's the same story. I do not want, if you want, I can repeat this exercise with 3 variables. If you want, I can repeat the same exercise. It will be the same story. Maybe I'll give it to you as a homework. I mean, that's a good idea, right? To give. Okay, great. So I'm going to give you this as a homework, right? As a mini project to simulate this for F1 and F2. And if you have issues, you can always ask the Wisconsin guy. Okay? Just not to submit, just just for your own kind of education. Okay? The same story what I did here, right? But in this case, you simulate the epsilon once again. Okay? So now what I want to do, I want to look on Z. I want to see, right, what is going to be my beta I. So what we are going to do now, we're going to find the variance of beta and we're going to compare it with the theoretical R. Okay? I mean, do you know JDeep? You know JDeep? Okay, so I think JDeep, who is going to teach you next semester? JDeep, right?
Yes.
Okay. He's going to teach you equity. So so the highest praise I got from JDeep, because in one meeting, not this year, but in a couple of years ago, right, he tells me, Yaakov, when I talk with them about regression, right, they know exactly what I'm talking about. So that's the biggest praise I could get, right?